We're going to start looking at graphing. To graph quadratic functions in vertex graphing form, you need to find the value of a, which tells you if the graph is if the graph is up or down, and it'll also tell you the width. You need the vertex, so this will tell you where to start your graph. You'll need to know the roots, also known as x-intercepts, solutions, zeros, which we'll learn this today, and our y-intercept. So just a quick review. The width, it tells you about the size of the parabola. If a equals 1 or -1, the graph is normal. If we are between -1 and 1, so pretty much if we just forget about the positive or the negative and just focus on the number, 1 is normal. A decimal between 0 and 1 is wide. And if that number is bigger than 1, we're narrow. So quick, just writing if we have a wide, narrow, or normal parabola. Here, our a value is 1, so this is normal. Here, our a value is a decimal between 0 and 1, so 1/3 written as a decimal will be 0.3 repeating, so this is wide. And here we have a 2 that's greater than 1. This parabola is narrow. In our next example, we have a decimal between 0 and 1. This is a wide parabola. Here we have a narrow parabola. 4 is greater than 1. And then here, our a value would be a 1. So this is normal. Our x-intercepts are the points where the graph crosses or touches the x-axis. So here they are in this picture, here and here. In this quadratic function, there are 2 x-intercepts. How many possible number of x-intercepts can a quadratic function have? So go ahead, think about that for a moment. How many x-intercepts could a quadratic function have? If you said that a quadratic function could have no x-intercepts, you would be right. This can happen in the following scenarios. So when I never touch the x-intercept, so I have 0 x-intercepts. We also have the possible solution where I just have 1 x-intercept, and that's where that vertex is right on the x-intercept. And then, like the example above, I have the possibility where there may be 2 x-intercepts, and that's the max. So our options are 0, 1, or 2. For the graph, determine the roots. So where am I crossing at the x-intercept? This is happening at 0 and 2. So our x-intercepts are at 0 and 2. You can write this as a point value, so 0 and 0, and 2 and 0. Here, our x-intercepts are happening at -1 and 6, so you can choose to write it as x-intercepts are -1, 6, or you can write them as their point values, -1 and 0, 6 and 0. A quadratic function can be written in the form, the vertex form. When we make y equals 0, we are now solving for a quadratic equation. When we find x, we have solved that quadratic equation. So the x values found are also called the following: x-intercepts, roots, 0. So if we want to solve for a quadratic equation, we're solving for those x-intercepts, and we have to set y to equal 0. So just letting you know, the question may be asked in different ways. It may be asking you to solve for the roots, or solve for the zeros, solve for the solution. It's all the same. We have to figure out who the x-intercepts are. Inadmissible solutions is a root of a quadratic equation that does not lead to a solution. And that's going to happen when we don't have an x-intercept. So that's going to happen in a scenario like the following. if the quadratic function is in vertex form, we let y equal 0, isolate the brackets, and then square root both sides. Remember to consider the two possibilities, that positive and the negative. So for example, remember that 2 times 2 is 4, but also negative 2 times negative 2 is 4. So here, let's put this into practice. Determine the x-intercepts of the following. So set y to equal 0. Okay, I need to isolate those brackets. So I have to move over this 18 by adding 18. So this can cancel out from the right side. And then I'm going to deal with that 2. And I'm going to do that by dividing by 2. Now those brackets are by themselves. So I've isolated those brackets. I need to get rid of that square. And the opposite of squaring is square rooting. And I have to consider both the positive and the negative. So here, when I get to this point, I have to write 2 possibilities. So 2 equations. One possibility is when I have 3, that's positive. And the second is when that 3 is negative. And you need to solve for both cases. So I got to solve for x. I'll add 4 to both sides so this can cancel out. And I get x is 7. And then in the other scenario where 3 is negative, add 4 to both sides. And I get that x is equal to 1. So here are my 2 x-intercepts, 7 and 1. Now we also need a y-intercept to help us graph. And our y-intercept is where it crosses on the y-axis. To find the y-intercept, let x equal 0 and solve for y. So here, if I want to do this example, set x to be 0 and solve. So the nice thing about the y-intercept is that it's easy. Y is already on its own. On the right side, we could type in our calculator. Negative 2 times itself is 4. And we get that y is equal to 7. So here's that point value, 0 and 7. Our domain is a set of all possible x values. Now our parabola goes forever and ever to the left and to the right. So the domain is a set of real numbers. This can be written as x belongs to real numbers, or in our brackets, negative infinity to infinity. It goes on forever, both left and right. So both to negative infinity and infinity. When a problem can be modeled by a quadratic function, the domain may need to be restricted to values that have meaning in the context of the problem. So when we deal with situational problems, sometimes we can't have values that go to negative infinity and infinity, and that's when we'll restrict our x values. We'll restrict our domain. Okay, the set of all possible y values is our range. Oh, here we go. Sorry, this little line here should be right here, which we learned about in our linear inequalities, that line stands for such that. Y, so if I wanted to read this out in English, it would say y such that y is greater or equal to negative 5, and y belongs to the real numbers. Or the other way of writing this, in this graph that we see, that vertex is the minimum, and that minimum is happening at negative 5. And the graph we just talked about goes on forever and ever, up and up and up, so that's going to infinity. We can write it as this. Now, the reason why we have a closed-in bracket is because negative 5 is a value. Infinity we can't even picture. It never ends. We leave an open bracket for that. So if I jump back to that domain, Notice that our negative infinity and infinity is written with open brackets, but because our y value has a value that we're starting at, it's going to have a closed bracket. So your range is all the y values. For the following 3 examples, determine the domain and range for each of the following. Well, domain is our easiest. Domain always goes from negative infinity to infinity. So I'm going to go ahead and fill that out for all 3 of my graphs. They go on forever and ever to the left and to the right. Now the range, if I look at this first example, we have a min, so that smallest point is starting at 2. I use my closed bracket, and if it goes on to positive infinity. Example in the middle, my highest point is at -1, and I'm going down to negative infinity. So my lowest number I start off with, negative infinity. My highest value is the -1. So then I end with -1, closed bracket. For example, on the right, my lowest point is -2, and my highest point goes on forever to positive infinity. There are my domain and ranges. For the following, determine the x and y intercepts, domain, and range. All right, let's start with our x-intercepts. Set y to equal 0, and then we need to isolate the bracket. So I'll add 8 to both sides. Always deal with our addition or subtraction first, and then our multiplication or division. So I got to get rid of the 2 by dividing by 2. Once our bracket is isolated, we have to undo that squaring. So we're a square root, and consider both the positive and the negative. So here I have to write the 2 possible equations when 2 is negative and when 2 is positive. Solve for x. So I have 2 x-intercepts for this graph. The y-intercept is much easier to solve for. We set x to equal 0. Okay, here I'm just kind of skipping steps. 4 squared is 16. And we get that our y value is 24. Domain and range. Domain, always negative infinity to infinity. Our range, when it's in the equation form, is maybe a bit harder to find, but if you do remember, we have to see if our graph is opening up or down. This one's opening up, so we have a min, and that y value is at -8. So our minimum is at -8, and this graph would go to infinity. There's our first example. Second example, set y to equal 0 to solve for my x-intercept. Subtract both sides by 7. And look at that, our graph or our bracket is already isolated, but guess what? We cannot square root a negative. There is no solution, which means there's no x-intercept. I can solve for my y-intercept. So set x to equal 0. And our y-intercept is at 16. Domain, always the same. And our range, this graph, once again, opens up. I have a min. The min value is at 7, and that graph goes to infinity. Okay, so here are some key points, and then you can work on your practice. The practice I'll just put in the note section in your Google Classroom. Oh, never mind. Here it is. Just kidding. Practice number 4, quadratic functions. All the questions on your home day, I'll have an activity. match the equations to the graphs.